Ben Brinitzer joined American Tower in March of this year to manage ATC's vast master antenna portfolio. He is a seasoned broadcast engineering executive with over three decades of leadership in RF systems, studio design, and technical operations across some of the most complex media markets in the United States. With a career spanning more than 30 years at iHeartMedia, Ben has overseen engineering operations for more than 40 markets across the country, managing teams of up to 65 professionals and driving innovation in both terrestrial and digital broadcasting infrastructure. He also has work published in Radio World, Broadcast Engineering Magazine, Radio Magazine, and he's shared his insights on HD radio installation, engineering, consolidation, and measurement procedures. He's also served on the FCC's Media Security and Reliability Council, MSRC, and contributed to several NRSC engineering policy councils. And with that, I'm going to give it over to Ben.
Let's get into master antenna design choices and discuss the agenda today. We're going to be talking Master Antenna 101. We've got a bunch of seasoned professionals in this room, so bear with me as we're going to start at the beginning and work toward the end. We're going to go over some system considerations, defining broadband antenna systems as a whole, the antenna types, transmission lines, combiners, requirements, benefits, etc. So let's talk a little bit about American Tower's fleet and the experience we've got with these systems, serving 36 television master antenna systems and 21 TV DMAs, with 35 of those being UHF after repack and one VHF system, and then 35 FM master antenna systems, and we're always looking to expand. So moving forward. So what are the goals of any antenna system? Those goals are get the signal to the audience, maximize population covered with the best signal levels, more height, more coverage, design pattern for best performance, optimize tower location. And there's a key point, guys. Tower location means everything. Minimize interference to other stations. Directionalize the pattern if needed. Operate under applicable FCC rules, of course. City of license coverage. ERP limits, how much power? So what about the broadband antenna systems? The master systems? Maximize coverage, tailor the antenna element arrangement for geography, decrease TPO to meet the required ERP, maximize signal saturation over the population, maximize number of stations in the system to decrease station CapEx and OpEx costs, decrease system losses, increase the gain, increase power handling. And we've got a few more goals. Minimize tower loading, reinforce your structure, reduce loading cross-section. One antenna serves multiple tenants, huge advantage. Minimize station costs, and this is a key point. Divide the capital costs across multiple users as well as the operation costs. That said, design components of the system. What type of antenna are we talking about? Top or side mount, slot or panel, horizontal, elliptical, or full circularly polarized, single or dual input. How about the transmission line? Rigid, flexible, rectangular, elliptical. And then finally, your combiner, star point, manifold, directional, branch, constant impedance. We're going to talk about all of these later in the presentation. So, antenna goal number 1, Some of you may remember these two as we saw them on a recent trip to Maine. Direct the RF energy as efficiently as possible over the desired coverage area. A couple of examples that are worth discussing. 7-station example we have here in a major market of television stations on a master antenna system. One thing you immediately notice is you've equalized the playing field and you've really covered the population well. So let's talk about the antenna types and arrangement of elements. Horizontal element position, how they're placed around the horizontal plane, determines the azimuth pattern. Omnidirectional, most of the time desired unless you have a directional license and have to protect somebody. Vertical element position, more elements, narrow the elevation beam width. More elements also give you higher gain, less TPOs required. Optimum spacing between a half and full wavelength. So, going to spend a few minutes on this. Pattern arrays and documentation, if you will. The azimuth pattern, in the beginning, when I first got into the business, azimuth elevation, what are we talking about here? Azimuth pattern, you're up in the sky, you're looking down at the earth, and you're drawing a circle for your coverage. Elevation is the, and I had a mentor way back when that very loved doing this demonstration. The for the elephant, basically, the elevation pattern is going to be straight off, down, vertical. Or to put it another way, vertically directed radio or RF. Antenna polarization. Horizontal polarization, TV, FM, LPFM, translators come to mind. Vertical polarization, LPFM, translators. I don't think there are any vertical only TV out there. Circular polarization, FM, and then elliptical polarization. Talking about the elliptical polarization, obviously your vertical's at a different ratio than 1:1. Couple of antenna examples to go through. Wraparound FM and VHF TV, commonly referred to as a panel antenna. Complex feed system, several rigid or flexible coax connections, provides greater capacity, superior performance, higher maintenance costs when compared to some of the other broadband antenna designs, can be more prone to failures, and will typically provide a cloverleaf pattern. So if you go back and you look at the azimuth pattern, that was a lima bean pattern displayed. Picture a cloverleaf instead. Can be directional. Another favorite type for FM is the side mount ring style or rototiller. There are several different flavors of this style. It provides circular polarization. It's very simplistic design, single feed system, extremely rugged, and typically low maintenance cost. Another one, TV radome panel. This one, commonly referred to as a panel antenna, complex, rigid, flexible internal feed system, as is pictured. limited repairability due to design and accessibility, horizontal or elliptical, cloverleaf or lima bean pattern capable, depending on panel placement. Another type, the pylon. Simplistic, internal rigid feed system, performance limited due to side mount, robust design, low failure rate, typically horizontal pattern, and lima bean. Here's a slide I'd like to spend a minute on. During repack, we took the opportunity to deploy a number of phase variable elliptical systems. And the cool thing about this is that by varying the phase, feeding the antenna between the two sides, you could adjust your polarization. More vertical, less vertical. And it was very easily achievable. It also, by its very design, provided redundancy capabilities. You lose part of the antenna, part of the combiner system, you're still operational. It's easily adjusted, and as mentioned, emergency redundancy. We have a number of these systems deployed. Antenna locations. Top mount obviously is preferred. The majority of master antennas are going to be top mount. And then there's the side mount. We've got a number of systems out there that are side mount and are auxiliary, some are main. The advantage of the top mount is obviously height. And as somebody used to say to me a long time ago, I'll take a foot over a watt any day of the week when it comes to coverage. Little to no pattern distortion at the top, and it's preferred for omnidirectional operation to eliminate the effects of the tower. I think Corey's going to have some interesting information on that a little later. It allows for stacking antennas on top of each other. It requires structural strength, no mounting pole, and it's generally a higher cost to install. Side mount uses the rest of the tower that's available. Some pattern distortion typically. It's difficult to truly make omnidirectional. It's leg or face mounted and allows for lighter antennas. So what's the transmission line goal? Carry the RF energy as efficiently as possible to the antenna with minimum wind load on the tower. How do we get it there? So some concepts. Construction material controls signal loss. It also controls cost. Typically, you'll see it in copper, aluminum, silver plating. Mode and power handling is determined by physical size. TEM is desired for coax. Fundamental transverse electric or transverse magnetic is desired for waveguide. More TPO, larger diameter or line count. Here's a key point that most of us miss until pretty late in our careers, until it comes up and bites you. Flange reflections due to fixed section lengths. Each flange has a small reflection. Randomizing links can disperse over the entire band. Hangers must allow, and I'm going to talk about that in a minute. Hangers must allow for thermal expansion, and pressurization is required to keep moisture out and can also impact voltage isolation ratings. Types. and bear with me on this one, we're simplistic, but coax, waveguide, hardline, hardline. Let's talk about the flange stacking, VSWR versus frequency. 20-foot sections will end up with flanges lining up at the same point in the wavelength multiple times, and you'll get reflections that occur at given frequencies. You'll see this is a chart covering what's basically the old TV band across the board. At the frequencies across the bottom, VSWR across the side, XY axis. And obviously, you don't want those kinds of reflections if your channels land on those frequencies. So the layout ends up being something like this. The list of channels that can fit the 20-foot line sections, list of channels that can fit 19 3/4 or 19 1/2. FM frequencies requiring 20 line sections, and requiring is probably the wrong word, but can use 20-foot sections is 88.1 to 95.9. You don't want it between 95.9 and 100 megahertz, basically, or you're going to regret it. So what do we do with the master antenna systems? We randomize the line so that the flanges never end up stacking consistently on the same channel or frequency. Here's a sweep of channels 20 through 43 VSWR versus frequency with line randomization. And as you can see, it's fairly consistent across the board. So waveguide also has critical links. Therefore, we typically don't use waveguide in master antenna systems, where our preference is going to be for coax. The velocity of propagation in waveguide varies with frequency and is more complex to calculate than coax. Each type of waveguide has its own set of line lengths to cover its band of operation. And consult the manufacturer because it varies. Here's an example of frequencies versus VSWR and lengths. So station combiner purpose. Put more than one station into an antenna. Important concepts for the station combiner. Isolation, minimize intermodulation products, independent operation. Consider the insertion laws, what materials are being used, the arrangement of your filters, the expandability, trade-off with expense versus size, versatile versus future-proof, the types, star point, branch, manifold, typically parallel connections at the output. They're not easily expandable. That is, until a certain manufacturer came up with a better design. Simple, small footprint, and it's very inexpensive. Constant impedance and directional. Constant impedance being CIF. Series output connection. Expandable broadband input. CIF is typically complex, duplicative in terms of filters, large and expensive. Waveguide directional, smaller, less expensive. So we have a bunch of seasoned folks in the audience. Anybody Care to guess on what type of combiner this is? It's going to be a branch FM to be exact. How about this one? This is going to be a CIF, constant impedance. You can tell by the hybrids on the input and output. What about this one? This is going to be a constant impedance directional filter. It's got some of the advantage of the constant impedance, while some of the advantages of the branch in terms of a smaller footprint. Bonus question. What kind of combiner is this? Correct. 13 station manifold. And I'm sure Corey's going to discuss this more a little later. All right, for the seasoned folks, what's this? Anybody? Nobody cares to guess? It's the constant impedance notch. Limits expandability. All combined signals must be known at the start. Early combiner technology, and it is no longer deployed. And by that, each of those canisters are notching out one frequency in this particular combiner. There were 5 stations. So some examples. 3 full power TV, 5 FM operations, taking up very little space on the structure. A couple of more examples with candelabras, 9 full power TV, 10 FM operations. Let's also talk about pressurization. One of the things that we do across the board is pressurize with nitrogen and nitrogen generators. In addition, we monitor the systems, both input and output, with alerting. Monitoring pulls it all together. Multiple critical items: combiner input status, VSWR, combiner output status, VSWR, room environmental temperatures, and pressurization. So to summarize, master antennas can be very beneficial to all broadcasters, operable over a wide frequency range, simultaneous operation for several independent TV or FM stations. It's mutually beneficial to everybody. Height on tower is shared. Gain typically is higher, so your bills are lower. CapEx is distributed across all members, as is the operating expense. And tower loading is reduced, so more can go on. One of the additional things that we do is provide broadcast and specialty construction. I'm sure if interested, Tiffany would love to discuss. And that sums up my presentation.
All right, let's have a round of applause for Ben.